Okay, in the previous video, we have talked about the four weaknesses in Bohr's atomic postulates. So the fourth weakness is the contradiction of Bohr's atomic postulates with Heisenberg uncertainty principle. We touch upon very lightly about Heisenberg's uncertainty principle in the previous video when we talked about the weaknesses of Bohr's atomic postulates. In this video, guys, we're going to look a little more detail about the Heisenberg uncertainty principle. So this is Heisenberg. So he proposed that um, from this mathematical equation. So delta x over here is the uncertainty in measuring position. So this is the uncertainty in measuring the position of the electrons. And then delta p is the uncertainty in measuring the momentum, or you can have it in delta mv as well to be written in that form. So you have the uncertainty for position and uncertainty for momentum, which is bigger or equals to the Planck's constants over 4 pi. So this is the principle represented mathematically. So what is it exactly? So according to Heisenberg, it says that it is impossible to know simultaneously both the position and the momentum of a particle with certain. So that means if you can know exactly the position, then your chance to know the exact momentum will be lesser and lesser. If you know exactly the momentum of the particle, if you are getting to know more about the momentum, then the knowledge about the positions of the electrons will become lesser and lesser. So you cannot, what Heisenberg is trying to say over here, it's impossible for you to know both exactly. Okay, you cannot do that. So you cannot you know exactly where the electron is, and then you know exactly what is the momentum of the particle. So that is proven mathematically by Heisenberg. And that is also what Bohr cannot explain and contradicts. It contradicts with modern um, quantum mechanical theory. Okay? So the next one that we're going to look at over here is what is the impact of that? Okay, so circular orbit is totally rejected by modern theories. So due to this theory over here, when they have been proven by series of experiments, so the circular orbit, the idea that you have this nucleus over here and you have this orbit. Okay, that is orbit. So this is the circular orbit. So this idea of circular orbit is totally rejected. So right now for modern theories, okay, we are no longer going to be using this. So this is only going to be applied for Bohr atomic model. Okay, for Bohr model, yes, we can use this idea of circular orbits, but when we want to talk about a much more complicated, much more um, accurate idea of this whole thing, we have to replace orbit with orbital. Okay, so we're going to use the word orbital a lot in the next asynchronous learning package. So this is what's going to be going on over here. So this is also the weaknesses, one of the weaknesses for um, Bohr's atomic postulates. Okay, the circular orbits is no longer going to be accepted, and it will be replaced by the idea of orbital. And then also, um, another addition to this knowledge over here is about the wave-particle duality of electrons, where de Broglie's postulate says that not only light, but all matter have a dual nature, and they can behave like wave and particle. Okay, so you and me, like light, we have our wave, and we are certainly behave like a particle. And the lighter you are, the higher is you would be the property of wave will be even more prominent when the matter is going to be lighter and lighter and lighter. So that is what de Broglie is trying to say over here. All matter will have dual nature. Light, like all matter, will possess or behave like a wave and particle. So it can be represented by this formula here. And we do know that this is the wavelength, and you have the Planck's constant, you have your mass, and you have your velocity. Okay, so that is the simple formula to represent the wave-particle duality. So that is a little bit about Heisenberg uncertainty principle and the de Broglie's principle for you guys to learn about. Okay, before we're going to move on to the quantum mechanical theory.